Pause and copy. Okay, so I want to find an area of a triangle, presumably use the property. So this triangle right now is floating in space away from the origin. So we're going to move it. We're going to move everything, A, B, and C, so that A ends up at the origin. Okay, so what we'll do is we will subtract, we're going to subtract 1, 2, 4 from everything. So let's write that. So 1, 2, 4 from all 3 points. Okay, that will preserve the area we're looking for, but it'll make our life a bit easier. So we'll get, we'll say A prime is now 0, 0, 0, right? B prime is 4, 3, 0. C prime is 2, 3, 3. Let me double check that. 4, 3, 0, 2, 3, 3. Okay. And they are situated in a better constellation because we can use our property so A prime is what's the origin there. So what we can do is we can think of this triangle that we're trying to sort out. We can think of it as a half of a parallelogram. So what do I want? Area is going to be 1/2 the area of the parallelogram. Parallelogram, which is 1/2 u v sine theta, but I don't want to use that, right? I want to use length of u cross v, where u can be that vector, v can be that vector. So they're defined by these 2 points up here, B prime and C prime. Okay, back to blue. What do we get? Get a half out front. Determinant I. Ooh, wait a second. We got all kinds of ugly stuff happening here. Let's do the length of, no, let's just do u cross v first of all. So my problem, why I'm pausing here is I have the u cross v, which involves a determinant, and then outside I have this length, and it's nested and it's not fun. So I'm going to do them separately. I, j, k. U, as I said, will be taken as from this point. 4, 3, 0. V will be taken from this point. 2, 3, 3. And what do you get? You get your I is 9. Your J is 12, but minus 12. And then your K is 6, 12, 12 minus 6, yeah. Factor out the 3. And we get 1/2 the length of 3 times 3 minus 4, 2. Make these lengths longer. So that's a half. Whoa. 1/2, no, 3. I'm going to take the 3 out. So 3 over 2 square root 9 plus 16 plus 4. 3 over 2 root 29. Yeah, good. Good job, Jordan. Okie dokie. Moving on. Oh, big gap. Okay. Pause and copy this theorem. Let's see. What should I say? Now, we've already found the volume of a parallelepiped, okay, which determined by u, v, and w. What we did is we took basically the transpose of this matrix, did a determinant, and then did an absolute value. Okay. So at least part of this is not surprising. Okay, I think what is worth talking about is the equal sign here. And it's a bit of a tedious proof. What I'm going to do is start with this thing, grind it out, and hopefully end up here. Okay, so I do it below here. Here's the first line, pause and copy. So I have u dot a cross product. Now I'm expanding the cross product in a funny way. What I'm saying is when you take I times this determinant, that ends up as the first entry in a vector here. And when you take j times this determinant, not forgetting the minus, you end up with this as a second entry, and so on and so forth. And now I have a dot product of two vectors, which I expand like so. Okay, just multiplying corresponding entries and summing. And now I want to recognize this as being itself a determinant. Maybe I'll just show you. So pause and copy. To understand this equal sign, I think it's easiest to go backwards. Okay, think about doing this determinant as a cofactor expansion across the first row, and then you'll get exactly this. Okay, so I've proven it. Well, I've proven what I wanted to prove. Okay, so I want you to find this volume. Pause and copy and try this exercise. I would call these things u, v, and w. And you're going to find the absolute value of u dot v cross w. Okay, the answer is 22. Let me know how that goes. Okay, here we have two lines. Now we're told, sorry, pause and copy. We are told that the plane contains both L1 and L2. Okay, that's very important information. If I pick two lines at random, there's no guarantee they will lie in a single plane. So let's see, I have a plane. Let's say it's like this. Oh. And we have L1, say going like this. And so we have L2 going like this. Now I want to find a normal equation for these this plane P. So what I'll do is I will call this vector u, and I'll call this vector v. And I will notice that if I have the origin, say down here, then one can imagine v going off like that, parallel to L2. And you can imagine u going off like that, parallel to L1. And if I do the cross product, imagining that u is behind the screen and v is right on the screen, if I use my right-hand rule, the cross product will go like that, and it will be normal to the plane P. So if I want a normal equation for P, a good place to start is define the normal vector u cross v. Now what was u again? 113. And what do we get here? 1 plus 3 is 4. And 1 minus 6 is negative 5, becoming plus. K is negative 1 by boop bop, like so. So how are we doing? 4 from, yeah. Okay, so here's our normal vector. And I can just use my formula, n dot x minus x naught is 0, becomes 4, 5 minus 3 dot x, y, z, subtracting what? Well, I need a point. I need a point on the plane. Where can I find such a thing? Well, the plane contains both lines, so it contains both of these points. I can use either one. I'll use this 727. Okay, again, 727 is on L2. L2 is in the plane. So 727 is on the plane. And I work this out, and I will get 4x plus 5y minus 3z is equal to 17.